So a lot of you have been very perplexed by this question that I asked in class on Wednesday. This is a classic physics question that is given to people, and it is a difficult one. It's really puzzling, and what I'm going to try to do is explain it here, hopefully in very understandable terms. So here's the problem. You've got a glass of water with some ice that's floating in it, right here, and it's filled all the way up to the rim. So the water is right at the top. Now the question is, what happens when the ice melts? Once it goes into melting, does the water level go up? Does it go down? Or does it stay the same? What's going to happen? How can we figure this out? So here we go. Let's talk about the ice that's floating in the water. When it's floating in the water, it is in equilibrium. It's not accelerating upward or downward. And what that means is that there must be a balance of forces. So the sum of the forces in the y direction equals 0. So there's a buoyant force pushing it upward, and there's the weight of the ice pushing it downward, okay? So if I set these guys equal to 0, then it basically means that they're same in magnitude, the buoyant force. And then this is the weight of the ice, mg, and this is the buoyant force caused by the water that is displaced by the ice. So we went over that earlier. So anything that's floating is basically going to displace an amount of water whose weight will be exactly equal to the object that's floating. So let's expand on that. So here we go. Let's look at these terms. So the buoyant force is equal to the density of water times the volume of ice that's submerged. In other words, that's the amount of water that's being displaced times g. So a density times a volume is going to give us some mass. All right, so that's basically the mass of the water that's displaced times g. That must equal exactly the weight of the ice. And the weight of the ice can be described as the density of the ice times the volume of the entire piece of ice. The whole thing, not just the amount that's submerged. This is a key point. That's the volume of the entire ice, whereas this is the volume of the water that's displaced by the ice cube, or by the ice under the water. So this is just the displaced water. This is the entire volume of the ice cube. Okay, so these guys are equal. All right, what does that mean? So we go a little bit further and just think about it. It turns out that this term here, the buoyant force, is nothing more than the weight of the displaced water. So you take all the water that's displaced by that ice and you weigh it, and it gives us this, the buoyant force. That's exactly what the buoyant force is going to be. But this over here is just the weight of the ice. These things must be equal. And now think about this. What does it mean if the weight of this displaced water is exactly equal to the weight of the ice? Well, let's go a little bit further with this. Here's a picture. So here's the ice, it's just floating, and that's the water that's displaced. I've just drawn it there. These guys have exactly the same weight. Well, how could they have the same weight? It's because they have exactly the same number of water molecules in them. Why is the ice a little bit bigger? Well, because the ice is less dense, so it's going to take up a larger volume. The water is more compact because it's slightly more dense. And so they have exactly the same number of water molecules, so when the ice melts, it's not going to increase the number of water molecules at all. And what that means is that as the ice melts, it basically changes from low density to higher density, and it takes up less space. And as it takes up less space, it doesn't cause the water level to go up at all. And so the water level stays the same. Hope this has been helpful. I'm very open to feedback, so please provide comments. Thank you.